Hello, welcome everybody to our third to last volcanic systems workshop. Thank you all for being here, and in particular our speakers for today as well as yesterday's speakers. As you saw, we have two talks today, and tomorrow we have a planning meeting scheduled for 12 to 2:30 Central Time. If you are interested to participate and haven't done so yet, you can sign up on the Modeling Collaboratory Volcanic Systems Workshop webpage. The agenda for tomorrow is first and foremost to discuss fairly specifically vision for the modeling collaboratory for subduction zone science with the focus on magmatic and volcanic systems. There will also be a breakout dedicated to an eruption response exercise associated with Converse, if that is something you're interested in participating in. So again, if you haven't signed up for that, please visit our website. It will be a separate link than the webinars themselves. And I will let Kyle Anderson introduce today's speakers.
Thanks, Haga. So our first speaker this morning is Mattia de Michieli Vitturi. Mattia is now an assistant professor at the University of Buffalo and senior scientist at the National Institute of Geophysics and Volcanology in Italy. He has a background in applied math, and his research interests are in the study and computational modeling of geological systems. So his research focuses on the development and application of efficient numerical models, which describe multi-phase and volcanic flow of many types, including plumes, tephra, lahars, pyroclastic flows, and magma ascent and volcanic conduits. Today, Mattia will present numerical modeling of magma ascent and volcanic conduits, equilibrium, and disequilibrium. Mattia?
Hi, so good morning, good afternoon, or good evening to everyone, depending on where you are in the world. So let me share my screen. So can you see the presentation full screen? Okay.
Yes.
And the point. Okay. So I think I can start. So before beginning with the presentation, just an information. So when I look at this Zoom presentation, I have always problems with the webcam of the presenter. I never know where to put that so that it will not cover the screen and the slides. And so in this case, I will always leave the space in the top right of the screen for the webcam and for the video, if you want to have the video open. And so now let's move to the real presentation. Volcanic activity represents a big risk for human population and the environment. And our capacity to mitigate the risk relies on our knowledge of the process that modulate magma ascent. Although controls on eruption style and scale are not well constrained, we know that physical and chemical changes on the magmatic mixture that occur in the shallow subsurface have a large control on the characteristic of the volcanic activity. But the problem is that we have always a limited possibility to observe directly what happens in a volcanic conduit. We have always a limited view, as for example in this video of the Volcano Villarica. And because of that, because of the limited view that we can have of the volcanic conduit, we have to rely on the interpretation of signals, as it was really well described on Tuesday for seismic signals, for example, or we have to rely on the modeling and numerical simulation of magma ascent. The dynamic of magma ascent in volcanic conduit is controlled by a wide range of processes, so by crystallization, degassing, outgassing, changes in magma rheology, fragmentation, and all these processes act at different temporal and spatial scale. Here we can see in the figure some of the processes. So we have a multi-disperse multi-phase flow where there are both bubbles and crystals that nucleate at some level. So below these levels, we have an homogeneous flow. And then we have this multi-phase flow where there could be horizontal gradients. And the coupling between the dynamic of nucleation and growth of crystals and bubbles and the associated change in rheology is what control at the end the transition in eruptive style. So the possibility to transition from an effusive eruption to an explosive eruption. The complexity of this multi-phase system is also reflected in the complexity of the mathematical and physical models. So in this slide, I would like to present some papers that presented some numerical models for Magma Ascent. This is just a real small selection because there are so many. But in any case, they will give you an idea of the wide range of processes that have been investigated with Magma Ascent modeling. Costa et al., for example, used a fully two-dimensional numerical model to study the thermal effects due to heat generation by viscous dissipation and loss to the walls by conduction. In another work, Costa et al. Introduced interconnected dikes and cylindrical geometries together with elastic wall rock deformation to study periodic variation in discharge rate. Massol and Joupart used the finite element model to solve the 2D governing equation for a compressive viscous liquid to study the details of magma extrusion in dome eruption. Laspina et al. Investigated the initial stage of explosive eruption using a 1D transient model for Magma Ascent. In this work, Caravana et al. Used a steady 1D model to study the mechanical stability of conduit and the relationship between magma rheology and conduit stability. Here in this work, I studied with other colleagues, I used a transient model to identify and quantify controls on the time scale and magnitude of cyclic volcanic eruptions. And in these final works, Dufek and Berkans modeled the transient two-dimensional dynamics in the upper conduit of a rhyolitic eruption to elucidate the role of particle collision in redistributing momentum after fragmentation. As we have seen, the number of processes which are involved in Magma Ascent and the number of models that have been developed so far is really large. And so it would be impossible today to touch all these aspects. And for this reason, I decided to focus on two things that I've called, as you can see here in the slide, the yin and yang of conduit modeling. So the first of these two, yin and yang, is the link between microscale and macroscale processes. So important processes like bubble and crystal nucleation and growth occurs at the microscale, but they have a large control on the macro scale. So the figure that we can see here show a volume rendering from an X-ray microtomography measurement of a stromboli scoria samples. And here in the top right, in the B panels, we can see the feldspar crystals that are shown, while in C, in the bottom left, we can see the void, the bubbles that are shown. And from this image, we can see a wide distribution of sizes and shapes for both crystals and bubbles. And it's important to remark that the effect of crystal and bubble on magma rheology is not only controlled by their volume fraction, the global volume fraction, but it's also influenced by their shape and size distribution. But how can we include this microscale description of crystal and bubble size distribution in the macroscale fluid dynamics modeling of Magma Ascent? And the other point I would like to touch and to present as another yin and yang of Magma Ascent models is the assumption of equilibrium and disequilibrium. A lot of time, equilibrium and disequilibrium are model assumption of models, but they should be model outcomes, not assumption. And they should be outcomes as a result of finite rates and of the ratio between different temporal scales, that of Magma Ascent and that of exsolution or crystallization. So the quantification of time scales for crystallization and exsolution processes through experiments and analysis of samples is fundamental to our understanding of such disequilibria and ascent dynamics. And to discuss about equilibrium and disequilibrium in Magma Ascent, I would like to start from the role of gas and the exsolution process. So in order to better understand the role of the gassing and outgassing, I would like first to derive some information from the simplest model we can imagine for Magma Ascent. Fluid dynamics model describing magma ascent are based on equations that represent the three fundamental physical processes: conservation of mass, conservation of linear momentum, and conservation of energy, also known as the first law of thermodynamics. For a volcanic conduit in each point occupied by the magmatic mixture, the mass conservation equation is written in the form that we can see here. So here we have a partial differential equation where rho mix is the mixture density and u is the mixture velocity vector. These equations simply state that in any controlled volume, the mass or the density increase because we have a gradient divergence in space of mass flux. In the simplest case that we can consider of a constant radius conduit, if this volume is the wall conduit and the flow is steady, we have that the inflow at the bottom of the conduit must equal the outflow of the top. And this is what is written here by this relationship. So density times velocity at the inlet must equal density times velocity at the outlet. This is in the case that we have a steady flow. And this simple relationship already has important implication for magma ascent dynamics. So let's consider a really simple example. For example, a 5-kilometer conduit, and let's consider an homogeneous mixture. All the phases have the same speed and same thermodynamic conditions, same pressure, same temperature, with a small quantity of exsolved gas at the bottom. So let's consider 0.6%, for example. Even without further exsolution, at atmospheric pressure, this quantity of gas expands, occupy at the end more than 90% of the volume at the vent. For this reason, the density of the mixture decreases considerably. And due to the equation written above here, we have that the speed must increase a lot. If we consider an equilibrium exsolution, so further exsolution during the rise, the volume fraction can reach 99%. With a rapid localized acceleration in the superficial conduit. So when the volume fraction increased from 0.5 to 99%, we have the velocity can change by more than 2 order of magnitudes, with a rapid and localized acceleration. From this consideration, it seems that magma is inevitably destined to fragment, producing an explosive eruption. But we know that it's not always the case. And so the thing is that we made a model that was too simple. As Einstein said, everything should be made as simple as possible, but no simpler. And why our model was too simple? Well, we assumed, first of all, single pressure for gas and melt, single velocity, and then no degassing at all, so complete disequilibrium, or equilibrium degassing. And so we want to relax this assumption, and in order to model disequilibrium and decoupling process. And in order to do that, we need to introduce in the model some additional equations and parameters. In particular, here I present 4 parameters, 4 characteristic times that control the degree of disequilibrium during magma ascent. These parameters reflect the time required to reduce the difference between the actual and the equilibrium value to a fraction of the initial values. And we have parameters, tau p, that control the pressure relaxation process, parameters controlling the disequilibrium degassing, a parameter controlling the disequilibrium crystallization, and another parameters which control the mechanical decoupling between the phases. For exsolution and crystallization, if these characteristic times that we denoted with tau are of the same order of magnitude or larger than the magma ascent time, this equilibrium process will affect the ascent dynamics. The characteristic time for crystallization and exsolution are usually function of pressure, temperature, dissolved water content, and bulk composition of the melt. But here, as a first order approximation, I will assume that these characteristic time are constant during the ascent. This doesn't mean that the gassing and crystallization rate are constant, because in any case, they depend on the degree of disequilibrium or the degree of supersaturation. And let's see how we define the gassing and crystallization rate through this characteristic time. And let's focus first on equilibrium and disequilibrium for gas solution. The degassing rate here is written as proportional to the supersaturation and as inversely proportional to the characteristic time tau d. Now, if the superscript EQ denote the equilibrium values of dissolved gas that comes, for example, from the Henry's law, for example, for dissolved gas, and if XD is the actual value, then what we have is that if we have an infinite characteristic time, then we will not have any exsolution, and so we will have a constant values for the exsolved gas. When the characteristic time becomes smaller, so the smaller is the value of tau d, the faster is the convergence toward the equilibrium value. And when the characteristic time goes to 0, then we have an instantaneous exsolution to the equilibrium value, which is controlled by pressure and temperature. The results that I will present in this first part of the talk were obtained with an open source Magma Ascent model, which is called Magma, which stands for Magma Ascent Mathematical Modeling and Analysis, where these disequilibrium decoupling parameters have been introduced. So in order to quantify the role of different processes occurring during magma ascent on the final magma vesicularity, here I used Magma to interpret the dynamics of dome-forming eruption. The Sulfur-Hills volcano dome-forming eruption provided a well-defined case study for an effusive eruption, because for this eruption we have both observation on the extrusion rate and also observation from the samples on the vesicularity of blocks from the dome collapse. And so here we see that this vesicularity ranged in the blocks from dome collapse from 0 to 45%. Now, before looking in details at the results of the numerical simulation, it can be useful to describe what the different plot that I will show represents. So, for example, in this plot, the velocity profiles are shown. Ascent velocity is plotted on the x-axis, while height from the bottom is plotted on the y-axis. When we allow for mechanical disequilibrium, so we will have three different velocity. Velocity for the liquid phase, which is represented in blue, velocity for the gas phase, which is represented in green, and the velocity of the mixture, which is represented by the red markers. When there is mechanical equilibrium, so when there is a really large drag, for example, these three velocities will collapse in a single line. And so we will see on the same line, the blue, the green, and the red markers. And so let's see the results of some numerical simulation. In this simulation, outgassing is modeled in follow with the Darcy law. And so we are allowed to have two velocities, and we have one single pressure for the two phases, and gas exsolution and crystallization are modeled at equilibrium. So the Darcy law is a phenomenological law that quantifies for laminar flows the slip velocity between the phases. And the equilibrium relative velocity between gas and melt is thus related to the vertical pressure gradient through the vertical permeability and the gas viscosity. And permeability is usually taken as a function of gas volume fraction. From the left to the right in this plot, we have the volume fraction of exsolved gas, the mass fraction of dissolved gas, the volumetric fraction of crystals, the phase velocities, and the pressures. And here it's important to remark that I'm plotting only the top 10 meters of the conduit. So what we can see from these results is that we obtain the porosity at the vent, which is more or less at 60%, and the mass flow rate, which is of the order of 3.5 times 10 to the 4th kilograms per second. So for this simulation, the mass flow rate is consistent with observation, but the gas volume fraction is larger than that observed in samples. In this simulation, we assumed an equilibrium degassing. So the characteristic time tau d was extremely small, but it's important to observe that even if the ascent rate was quite low, the decompression rate varied a lot during the ascent. And so this could lead to disequilibrium in the solution in the shallow part of the conduit. So why not looking at model results when we have a finite rate solution, so a larger values of tau d, which should result in a less gas solved with respect to the previous case. So with a finite rate solution with the larger values of tau d, we expect a lower porosity at the vent when the gassing is limited, and thus a better agreement with observations. But first of all, we need to constrain this characteristic time for the exsolution, the parameters tau d that I introduced before. And this has been done by comparing model results with isothermal decompression experiments as those of Magma and Sisson. In the experiment, Magma initially at 200 megapascal and with an initial dissolved water content of 5.2 water percent was decompressed at different rates and quenched at several final pressure. In the figure here, the final dissolved water is plotted, so it's the value on the x-axis, and the different symbols represent different decompression rates, while the solid line represents the equilibrium values of dissolved water. So we can see that changing the decompression rate, so increasing the decompression rate, we have values that diverge more from the equilibrium line. And for very high decompression rate, we have almost constant values of dissolved water, which are represented here by the black dots. In the model, the decompression rate is not an input parameter, so we can fix the inlet pressure, we can fix the initial content of dissolved water, but the decompression rate has to be an outcome of the model. And one way to obtain different decompression rate is to change, for example, the conduit radius, because different radius affect the ascent velocity. Ascent velocity increases with increasing radius. So different characteristic times, different values of tau d were tested, and it was found that values of 10 to the third seconds well reproduce the amount of dissolved water in the melt for the different decompression rates. On the left, you can see results of the numerical simulation where we changed the radius. So different lines are for different radius, which correspond to different average decompression rate. And so these decompression rates were similar to that were explored in the experiments. And also the amount of dissolved water using characteristic time for exsolution of 10 to the third gave amount of water dissolved in the melt at the different pressure that was similar to that obtained in the experiments. So it was a good constraint, a good estimate for the characteristics, the exsolution rate. So we repeated the simulation, in this case, not just with two velocity through the Darcy law, but also allowing for gas exsolution at a finite rate. And when we do that, we observe that because of the change in magma ascent velocity and magma pressure, the compression rate increased from bottom to the top. So in this plot, we can see on the x-axis the decompression rate, and here the depth. And there are also some markers that denote the timing of the ascent. And we can see that the compression rate increased a lot in the last hours. And so with this decompression rate, we have disequilibrium exsolution, and this disequilibrium exsolution is shown also here by the difference in the actual values of dissolved gas, which is represented by the blue line, and the equilibrium values represented by the red dots. And so let's see if adding disequilibrium, so if implementing a finite rate exsolution, we have a lower gas volume fraction at the top. That was the results that we want to obtain it, because it was what was observed at the blocks, at the samples from the Safaris volcanoes dorm building eruption. So in the left panel in this figure, we plotted the gas volume fraction at the conduit exit here on the y-axis as a function of the logarithm of the characteristic time of exsolution. So we move from 10 to the -4 to 10 to the 4. And we see that when we move from the left to the top, we are moving from equilibrium exsolution to disequilibrium exsolution. And what we observe here is that, so we have said that when we move from equilibrium to disequilibrium, we are reducing the amount of gas exsolution. But what we observe is that what happens is that the gas volume fraction at the top increases. This is quite strange. It's not something that is obvious, but this is due to the fact that it's due to the complex interaction between degassing, outgassing, and magma rising. In fact, reducing degassing leaves more volatiles dissolved in the melt, decreasing melt viscosity, and thus producing a faster rise in the conduit. So when the parameter, the characteristic time tau d, increases in the investigated range, outgassing is less efficient for high ascent rate, and more gas remain in the magma mixture. So outgassing plays an important role in this kind of eruption, and the link between outgassing and degassing is really important. And so we investigated different permeability models. Rust and Cashman, 2004, for example, recognized that the relationship between pressure gradient and gas flow is not linear, as described by the Darcy law, and they proposed to use the Forchheimer correction to the Darcy law, where there is an additional inertia permeability. Again, we have to understand that permeability is something that develops and occurs at the micro scale, and we model it lumping this microscale process in the constant, that it's called the inertial permeability, which account for a lot of parameters, a lot of things like the influence of the geometry of the network of bubbles, the connected porosity, the throat radius between the coalesced bubbles, the bubble number density. So we used this correction, the Forchheimer correction, and this was not something new. The Forchheimer correction for Darcy law was already used by the Gruiter et al., for example, when they investigated the role of permeability on the transition between effusive and explosive eruption. And so here we can see a final plot where we can see that when we use the Forchheimer law instead of the Darcy law, and again the gas exsolution that was at a finite rate with a characteristic time constrained by laboratory experiments, finally we obtain a good agreement with observation, both in terms of mass flow rate and at porosity at the vent. Here in this case, we are plotting only the top 50 meters of the conduit, and we can see here in this plot that we are modeling disequilibrium in the exsolution, because the actual values represented by the blue line is going far and far from the equilibrium value represented by the red plots. And also here in this plot, we can see the decoupling between the velocity associated with the permeability relationship that we are using. These simple exercise highlight on one side the importance of the implementation of finite rate for exsolution that allow to model disequilibrium, and the other side, the complex interaction between processes that occur during magma ascent, like degassing, outgassing, and viscosity. So far, I discussed only the role of gas on the dynamics of magma ascent, but it is well known that crystals also, together with bubbles, play a fundamental role in modulating the large scale dynamics of magma ascent. The basic concept of crystallization and crystal size distribution are well reviewed by Marsh 98, for example, or Hammer 2008. And also there is a really great review paper published the past year, I think, by Katie Cashman on Frontiers on the advances and challenges of crystal size distribution analysis, which assess the extent to which experiments replicate observed crystal population. Here I want just to present a few examples of how a finite rate of crystallization has been implemented in numerical model of magma ascent. So again, what is the role of a finite rate which in some way affect the equilibrium and disequilibrium in crystallization? Kozzono and Koyaguchi modeled in a work of 2012 the effect of both gas escape and crystallization to understand the complexity of conduit flow dynamics during lava dome eruption, and they adopted a formulation for the crystallization rate that is similar to that we have described before for gas exsolution, that you can see here in this equation. Here, beta is the volume fraction of crystals, and you can see that the rate of crystallization is proportional to the difference between the actual values and the equilibrium values, and is proportional also to this constant gamma. Gamma here is a constant that represents the inverse of the time scale of crystal growth, and the values in this work were based on the experiment data of crystallization kinetics by Couch et al. In 2003. Here we can see these two figures where we have two different lines, both on the left and on the right, and the two different lines correspond to two different values of this constant crystallization constant. So two different values of the capital gamma. And these figures highlight how the different time scale for crystallization produce different thresholds for the transition between dome eruption and explosive eruption. We remark here that adopting a crystallization relaxation parameter, as it was done here in this equation, and as it was done, for example, also for the bubble, for the gas exsolution in the previous model that I've shown, is not the only strategy to model crystallization or gas exsolution rate. So for example, Manneke, Sparks, and Costa, in their model, they used an integral equation that constrained magma under cooling and split crystal growth in the formation of new crystals and growth of existing crystals, which allow producing a more complex set of numerical results. And so these allow to have a better comparison with petrological information. Another model where a similar formulation to that we have seen in the previous slide is that is presented, for example, in La Spina et al. 2016, where a similar formulation, again based on the difference between the equilibrium values and the actual values and constant crystallization time, constant crystallization rate, was used to simulate the Mount Etna 2001 flank eruption and to constrain time scale of crystallization. During this eruption, two different kinds of products were observed. A plagioclase-rich magma with a high crystal content that was erupted from the vent located above 2,600 meters above the sea level, and also a plagioclase-poor magma with a low crystal content. It was erupted from a lower vent, and in this application of the model, La Spina et al. Considered three different crystal components: plagioclase, clinopyroxene, and olivine, and two different volatile species. Each of them accounted in the numerical simulation, and for each of them there were finite crystallization and exsolution rate. In this figure from their work, we can see the final volume fraction for the three crystal components, so the volume fraction at the vent, as a function of the characteristic time of exsolution at the gassing. So we have here on the x-axis the characteristic time for crystallization, on the y-axis the characteristic time for exsolution. And the different colors represent the crystal content for the different crystal components, for plagioclase, pyroxene, olivine, and then the total one. So in this way, it was possible, using these numerical results, to constrain the crystallization time scales. And in addition, this modeling allowed, and the results suggested that the relative high plagioclase content that was erupted from the upper vent required a long time of crystallization, and thus suggested the presence of a shallow reservoir. Similar approach was also used in this other work by Arzilli et al., so a recent work of 2 years ago, where the crystallization times were not constrained by the comparison with samples, but mostly by using fast synchrotron X-ray microtomography crystallization kinetic experiments that were used to quantify the characteristic time of plagioclase and pyroxene crystallization in basaltic magmas. The results obtained during a rapid and continuous undercooling were used in Magma Ascent model to study the condition leading to basaltic plane eruption, in particular with condition appropriate for Mount Etna. The combination of these experiments, observations, so in situ experimental observation, and the use of numerical models allow it to constrain again the characteristic time and also the pre-eruptive temperatures that can favor the formation of highly explosive basaltic eruptions, such as Plinian volcanism, which are driven by fast syneruptive crystal growth, even at high decompression rates. And so these papers show how experiments can inform numerical models and can help to better constrain the temporal scale of the processes that we want to simulate. So far, I've only discussed one of the two, yin and yang, that I have introduced at the beginning, and in particular the equilibrium and disequilibrium, and how this is controlled by the crystallization or the degassing times, characteristic times. And I've done that presenting the results of several Magma Ascent models. But one of the main limitations of all these models and approaches presented so far is that in all these models, both exsolved gas and crystal phases were always described through an integral quantity, the volume fraction. And this describing the description just through the volume fraction, so doesn't give any information on the polydispersed nature of bubbles and crystals. But as a matter of fact, we know that nucleation and continuous growth results in bubble and crystal size distribution that continuously change in time and space during the ascent. And this change in crystal and bubble size distribution exert a first order control on magma rheology, so on magma ascent dynamics, and finally on the eruptive style. For example, Cimarelli et al. Performed experiments with analog material, and they show the important effect of crystal polydispersity for both the size and shape in determining magma viscosity. In their experiments and their data show that increasing the relative proportion of small elongate crystals to large equant crystals at a constant total volume of fraction can increase the relative viscosity by up to 3 orders of magnitude. So for this reason, I would like also to present several works that tried to model the evolution of bubble and crystal size distribution. And these works also tried to highlight the control of the bubble and crystal size distribution on Magma Ascent. For bubble size distribution, an important work is that done by Toramaru, who used a set of equations that were derived for the crystallization by Randolph and Larson, where the moments of size distribution were introduced to describe integral properties of those distributions. The heart of this method of moments is the development of a population balance equation that describes changes in number and size of bubbles, and then the derivation from this population balance equation of transport equation for the moments. And the moments are the quantity that are described here by this equation. So are integral quantity of the bubble size distribution, which is represented by this function that is introduced here. So Toramaru performed a numerical simulation with a constant decompression rate and highlighted two different regimes in nucleation and growth process, which results in different bubble number density. So there is a diffusion controlled regime and a viscosity controlled regime. And with these two different regimes, we have different number density of bubbles. So there is here you can see that the order of magnitude is 10 to the minus 17, while in this case 10 to the minus 12. So a quite large difference. And this is possible to simulate these things only if we write an equation for the bubble number density. So only if we account for the bubble size distribution in the model. In addition, he also showed that if magma is quenched immediately at atmospheric pressure, the volume fraction also is much smaller in the viscosity limited growth case than in the diffusion limited growth case. Now a rapid fast forward to another paper that considered the bubble size distribution together with the Magma Ascent. So in this recent paper of Mirza and et al., 2021, so very recent, they simulated bubble nucleation and growth during Magma Ascent. As in the work of Toramaru, the method of moments was used to track the evolution of bubble size distribution. due to the growth of existing bubbles and also due to the heterogeneous nucleation, in this case, in this work, facilitated by magnetite crystals. In this way, they show that it has been possible to reconcile bubble nucleation in explosive eruption with the geospeedometers. And I would like to point out again here, so if we look at these figures from their results, that we can observe that the decompression rate here in this plot, the blue line, the compression rate is not constant, but it increases as water exsolves and as viscosity increases. And so in this way, coupling all these processes, model simulation account for this time-dependent magma decompression, and they can predict multiple nucleation events. Like we can see here, this second nucleation, that it's in response also to this large decompression rate. For what concerns the evolution of crystal size distribution, the work of Marsh in '88 provided the theoretical basis for most crystal size distribution studies and of natural and experimental samples. Here I would like just to present a couple of important works, 2 or 3 important works, which tried to couple fluid dynamics model with model describing the evolution of crystal size distribution, or at least that tried to give a contribution in this direction. One notable example is the work of Melnik et al. In 2011, where they developed a model to interpret crystal size distribution produced in steady eruption that was based on the assumption of a crystal growth rate. So based on this assumption of constant growth rate of crystals, from the final crystal size distribution that is observed, for example, in samples. So this is the crystal size distribution at the vent. Because of the assumption of constant growth rate, they could go back in time or in space, and so they could compute at each depth the number of crystals associated to each sides. And this model was used to obtain the distribution of parameters with depth from a measured crystal size distribution, and it was applied to plagioclase crystal size distribution obtained from a sample from the 1984 lava dome building eruption of Mount St. Helens volcano. In Melnik work that we have just seen, the crystal growth rate is constant, while in the previous works presented today, like the Cozzone and Koyaguchi, La Spina, crystallization rate was a linear function of supersaturation. But there are some other recent work, like this one, for example, from Befus and Andrews, where they presented the results of decompression experiments to link growth and nucleation of plagioclase microlight to the degree of saturation, supersaturation. The solid line in this plot represents the instantaneous linear plagioclase growth rate as a function of supersaturation and show a non-linear dependence. And so for this reason, they proposed a different functional form, a log normal functional form, to represent the growth rate and as a function of the supersaturation. They also presented a crystallization model, and they show that, I'm citing now their paper, that crystallization produces an ever-evolving supersaturation or disequilibrium that in turn result in significant disparities between instantaneous and average nucleation and growth rate. So again, it's important to understand that when we do the modeling, so we couple all these processes, we can have large variation of both nucleation and growth rate and decompression rate of all these things during the ascent. And so we have a lot of disparities between the instantaneous and the average nucleation and growth rate. Now, a final model that I would like to present is this one by Colucci et al., where a new predictive model, again based on the method of moments, was developed for studying the kinetic of crystallization in volcanic system. The model was applied here to simulate the evolution of a crystal size distribution for a ternary system, and in particular, cooling experiments at atmospheric pressure performed on stromboli lavas were used to validate the model. One notable feature of this model is that it takes into account also the change in the melt's composition with the crystallization, which on one side control the liquidus and solidus surface and thus the nucleation and growth rate, But on the other side, we have to consider that if we change the melt composition with the crystallization, and this is something that is usually not taken into account in Magma Ascent model, then this could produce also important changes in melt viscosity. So the consideration of these processes would be important when we want to properly model the change in viscosity associated with the crystallization. So just to conclude now, I think it's worth to quote a famous quote from George Box, who stated in a 1976 article that all models are wrong, which means that a given model will never be able to represent the exact real behavior. That said, even if a mathematical model cannot exactly describe all aspects of the dynamics magma rising in a volcanic conduit, we have seen that when the most important processes are considered, then model can produce results that are quite close to reality. And in fact, also George Box repeated these aphorisms a few years later in a second article, containing a section that was titled, "All models are wrong, but some are useful." And so also in our case, we started from the simplest model, and then we added more physics, more process, better constitutive equation. And at the end, we were able to reproduce a lot of observation of natural samples. So a few conclusions about what I presented. So despite the present limitation and simplification, conduit modeling is able to provide useful information for understanding volcanic system. The modeling results that I've shown highlighted the complex interdependent mechanisms that modulate magma ascent, like the gassing, outgassing process, magma crystallization, and the associated changes in rheology. In general, current conduit models are able to discern conditions that lead to different eruptive styles and scale, and so they can help to contribute, and they can contribute to volcanic hazard assessment and maybe forecasting. We remark, however, that some major partially unsolved challenges still persist. So among them, the need of continuing to develop approaches that produce quantities that can be immediately related to data derived from geological, geophysical, and geochemical analysis, as was highlighted in a paper from Polacci et al. In 2017. Valuable examples of such quantity include the crystal and bubble size distribution, as we have seen, but also other parameters as magma ascent related geophysical and geochemical signals, including those that are associated with the transient phase of conduit formation and eruption waning. I would like just to conclude with a sort of joke that it's called spherical horses. So I know that in geology, usually, so there is a similar thing, but with spherical cows. But my background is mathematics. So in mathematics, in the field of mathematics, there was this joke on spherical horses. And so there was a wealthy gentleman that had an uncontrolled passion for horse racing and for betting on horse racing. But he hardly ever won. And so he decided to offer a prize to anyone able to provide him a method to win with certainty. So a mathematician, attracted more by the scientific challenge than by the money, accepted the challenge. After months of hard work, he was convinced that he had found a model that worked. He showed up at the house of the millionaire, claiming that he had the solution. And when the millionaire asked for a detailed description of the method, the mathematician started to present his model. And so presented his model in this way. Oh, let's first assume that all horses are spherical. And so this is just a joke, but here there is something that I took for a paper that I wrote. So I'm not, anybody else has to complain, but most of the papers on conduit modeling start in this way. The analysis presented here consider only cylindrical conduits. So when we consider cylindrical conduits, is it that something like the spherical horses? Well, maybe not, but that means that there is still a lot of work to be done if we want to proper modeling magma ascent in volcanic conduit. Thank you.
Thanks, Mattia. That was a really great talk, questioning a lot of the assumptions and simplifications that we make in these models. We're a bit short on time, so I'll just ask one question for now, and you can answer the rest in the chat.
Yes.
From the first one from Tobias Keller. the models you show assume unidirectional flow in the conduit. And is that a good assumption, particularly for low viscosity, persistently active systems? And how does bidirectional flow factor into our understanding?
Yes, I agree that this is a simplification, and it's one of the simplification. I don't know if it's like the simplification of the spherical ores or not, but it's something that we have to work on. So there are several models that I presented at the beginning that consider also 2D phase flow. So when we have a highly viscous flow, like for example with high viscosity, then we can assume that we have a laminar flow, and so we can consider an average velocity. So in this case, maybe the assumption is good, but then in some case, also when we have more complex geometry, probably multidimensional models should be considered.
All right, thank you. As she said, unfortunately, we'll have to move on, but thanks again, Mattia, for an excellent talk. And feel free to ask questions in the Q&A box of Mattia or our next speaker as she talks. And you don't have to wait until the end. You can go ahead and ask your questions as the presentation goes on. So our next speaker is Madison Myers. Madison is an assistant professor at Montana State University, conveniently located just outside Yellowstone. As a volcanologist, her research combines extensive field sampling and petrologic techniques to investigate storage triggering and dynamics of explosive eruptions. Much of her work is focused on caldera-forming events. She often pairs melts and mineral chemistry with diffusion models to extract processes and timescales. Today, Madison will present Rates of Magma Ascent, a Petrological Perspective. Madison?
Thank you so much, Kyle and Helge, for that introduction and for putting together such an amazing series of talks. So today I'm going to close up our conversation around magma ascent, providing a petrologic perspective based largely on field data and how we might use different tools, their limitations, as well as advancements that we're making to understand something about what's happening within the conduit system. To start off, I want to pose the somewhat simple question, especially after Mattia's wonderful talk, of what does magma ascent control? What is our goal? We're trying to determine magma ascent from an eruptive product. And many of you might automatically think, well, it's simply put, it largely controls the style of eruption that we see at the surface, where slower ascent rates are thought to lead to more effusive eruptions, and faster ascent rates tend to lead to more explosive eruptions. The reason this might be easy to kind of get it in your head is that there's been numerous studies to support this kind of understanding of how magma ascent controls eruptive behavior. And this is largely due to the fact that as magma ascends towards the surface, gas is going to exhaust from the water and other volatiles that were dissolved within the melt due to the reduced pressure as it approaches the fragmentation front. And like Mattia just went over in great detail, depending on how they behave, if they stay stuck within the melt or if they decouple from it in some kind of disequilibrium process, this largely is going to control how explosive an eruption is. So the more tantalizing question then might become, well, what controls magma ascent? And this is not my question. This is the question that Dr. Heather Wright seems to ask after every talk I give, and is potentially what we're all trying to seek with these series of talks this week. This, of course, is a much more complicated question that we have been approaching from different angles, and that's because it can be due to differences in the storage region into the overpressure that's feeding into the conduit system. It can be due to shifts that are happening within the conduit system as gas exsolves, forming permeable networks, or directly related to crystallization that's occurring within the conduit system. And of course, these are all complex feedback systems on each other, so that as you have competing effects of viscosity or strain rate or the development of permeability, you're going to cause shifts within magma ascent rate. And this is nicely illustrated in this Cassidy et al. 2018 paper. So just to summarize this idea is that, well, the rate at which magma ascends strongly influences the eruptive behavior that we see at the surface, thus something that we really want to understand. However, it's extremely challenging to constrain these rates because so many different regions are going to influence them, including the geometry of the conduit system. However, from a field geologist point of view, we don't often have a lot of tools at our disposal besides the complex field deposit to try to extract these rates and what regions might be influencing the evolution of the system, leading to these diverse field deposits that we're seeing. This is, of course, complicated by the fact that different systems are going to require completely different tools to be able to quantify timescales and conduit processes, meaning that we need recorders that will respond to different compositions, different rates, and different kind of crystallinity systems to be able to extract these processes. So before going into the details of all the petrologic tools that have been applied and the advancements we made, I want to highlight first off that from the field geologist perspective, typically the best type of material to use to reconstruct conduit process is material that is rapidly quenched against the cool air, meaning something like an airfall deposit, which as that plume goes up, it's interacting and quenching quite quickly, meaning it's largely going to preserve the history of the conduit system. So this might be pumice clasts that fall out into an airfall deposit. Other systems like ignimbrite formation or a lava flow, you can still retrieve this information, but you do have to be cautious about the fact that there can be post-emplacement effects that might overwrite or add an additional signal onto whatever you're trying to extract from that conduit process. And so you do have to then be wary to subtract any kind of modification that could occur post-emplacement. To start off with, I'm going to go over the two kind of most common earlier developed tools that we use to try to understand magma decompression and ascent rates. The first is, of course, microlights, which Mattia nicely presented a lot of studies on microlight growth. The idea behind this is that the rate at which microlights grow and their distribution is directly related to that degassing that's occurring within the conduit system. And so you can calibrate the number and size that you're seeing using experiments to understand something about the amount of time that this material spent within the conduit system. And so this, of course, is important to quantify for different compositions that you might have, different temperatures, in order to then say what was the decompression timescale. Similarly, this is an example of an amphibole breakdown rim from Rutherford and Hill, 1993. And what's happening here is that a hydrous mineral is interacting with a lower water concentration melt, again, something that's going to occur in the conduit system as water exalts into gas bubbles, and it's breaking down due to being unstable within that environment. And so the thickness of this rim is going to give you some information about how long that amphibole spent in lower water environments. Importantly, both of these two methods are essentially need to be kind of calibrated in order to be able to use them to extract timescales and then to assume some kind of magma ascent timescale based on the amount of time they spent in the conduit system. These processes are going to be more reactive at higher temperatures and lower viscosities, meaning that you can get at faster ascent rates in higher temperature systems. So when you start to go into more evolved, cooler systems, these processes are going to be suppressed and slower, meaning the timescales that you're going to be able to extract from them are going to thus be slower. And this is going to be an important theme of the talk, is that many of these petrologic tools are going to be rate limited. So for silicic systems, the tools that have been more classically used include bubble number density, following up on the experiments that Torimaru has done to quantify how the number of bubbles that you have within your system is directly related to decompression rate. This, of course, becomes complicated by the fact that during slower decompression, bubbles will coalesce. It's also complicated by the fact that as you approach the fragmentation level, you can have a second nucleation event that might then weight this process to a specific region of the conduit system. Another tool that has been frequently used that more gets at mass discharge rate and plume height rather than necessarily magma ascent rate, although they are related, is to look at the distance of which material has fallen from a vent, meaning that a bigger plume is going to have larger clasts that fall more proximally towards a vent. And you can then use isopac and isopac mapping to reconstruct the plume height as well as the mass discharge rate of these systems. The nice things about all of these methods is that you can apply them throughout a sequence of your deposit to reconstruct how the dynamics might be shifting over time. But importantly, and I really like this term that was used in Casa et al. 2020's review paper, these are reaction chronometers, especially these upper two and this bubble number density, meaning that they are reacting to the loss of water within the conduit system. They're not directly recording the ascent, they are reacting to that process, and you can extract a time frame from them and then assume some sort of magma ascent dynamics. And as Mattia said, by coupling this with a numerical model, you can then really start to repiece some of the actions that are happening within the system. An example of that, and there are numerous examples of this, is to take a complex field deposit and to be able to sample within multiple layers within that deposit to look at how texture, things like crystal size distribution, bubble number density have shifted over the course of the eruption, giving you a lot of data to integrate into understanding how the dynamics in the conduit might shift during any eruptive period. In this case, from this example from Gardner, 1998, they also had seismic data, meaning that they were able to use with the onset of seismicity and understanding where the depth of the magma chamber was to calculate a magma ascent rate and couple that with their textural analysis. And so this is, of course, a really kind of the dream situation in that you can understand exactly how that textural formation is going to relate to magma ascent timescales. However, of course, most field geologists have had to accept the fact that in a lot of situations, we do not have seismic data or independent data to constrain magma ascent rate, again, requiring us to go to the deposits and try to determine how magma ascent rate has shifted over the course of the eruption and integrate this textural data to try to figure out which regions of the conduit might be, or even the storage region, might be influencing these rates. One, of course, huge advancement that has been made in the field of petrology is crystal-specific diffusion modeling. And so this is a review from Casa et al. 2020. And what we see on the y-axis here is the resolvable timescales, the timescales of interest that you can extract from a crystal. And on the x-axis, there are different mineral phases, as well as in these boxes are the element species that would be diffusing on the timescale of interest. Importantly, we have developed so many tools and techniques and have done experiments to kind of confirm a lot of the rates at which these processes occur, but most of them largely are going to tell you about timescales of residence, mixing, and perhaps triggering, but most of them don't tell you about magma ascent timescales. You'll notice here that magma ascent timescales, which are often on the order of hours to days, the two kind of obvious things here that you could use are both based on water loss. So again, the same kind of triggering mechanism of water exsolving into a gas phase, causing diffusion within these species. This, of course, is a ripe area that I think is becoming more and more developed over time and is probably where a lot of our community is going to be focusing its energy, is to looking at these quick diffusive species that are going to react to conduit processes to extract timescale. Two examples of that on the left, this is Newcomb et al. 2020, and this is looking at natural samples where they measured water profiles within olivine to extract ascent timescales. This, of course, requires, again, experiments to confirm the diffusion coefficients that are used to model these profiles, but seem to give results that pair with other speedometers, suggesting that it is a method that can be used to extract magma ascent rate throughout a deposit. Of course, you would then require a system that has olivine, just like most of these have a requirement based on what you have to work with. On the right-hand side, this is an example from Lee et al. 2020, and this is based in apatite, where this is experimental data where they looked at the rates of chlorine, fluorine, and water diffusion in apatite crystals to also extract magma ascent timescales. And I would largely argue that this is where a lot of the advancements, I think, in the petrology field are going to come into. Another technique that I am slightly biased towards is looking at water, CO2, and sulfur gradients within melt pockets or reentrants. The advantage of this technique is that it's been found to be reliable as a way of extracting magma ascent timescales from olivine-hosted reentrants, which you can see on the right-hand side. This is an example from Fuego. all the way up to more evolved systems. On the left-hand side, this is an example of a melt reentrant in a plagioclase crystal from Mount St. Helens. And so again, just to really beat a dead horse, so during decompression, gas is dissolving into bubbles and it's driving water, CO2, and sulfur into this gas, creating gradients that you actually are measuring and modeling to come up with magma decompression and ascent timescales. Again, the advantage of this technique is the fact that you can go all the way from rhyolite to basalt and to extract magma ascent timescales. You also have pretty good constraints on the diffusivities in most of these compositions in order to be able to extract these timescales. Of course, the limitation, just like with everything, is that you have to find these melt reentrants to be able to extract this timescale. The nice thing is that if you can apply the same method to multiple different systems, you might be able to start to say larger kind of statements about how magma ascent might relate to other parameters. So here's an example from Barth et al. 2019, where they looked at multiple different, mostly basaltic systems and compared decompression rate versus, versus mass eruption rate. And what they found here was, this is a study looking both at water diffusion within olivine as well as melt reentrants. And you can see that there's a very nice trend of increased decompression rate with mass eruption rate. This, of course, breaks down if you start to add other caldera-forming eruptions into it, but it does give this idea that we might be able to start to look at different systems, even the same system, different eruptive episodes, to try to understand, are there fundamental links between decompression rate and mass eruption rate? Another compilation by Shea 2017 looked at bubble number density. So we have mass discharge rate on the x-axis and decompression rate on the y-axis. And this is based on comparing bubble number density to that tomorrow experimental data. And here you can see that there's much less of a kind of correlation in the data set, where bubble number density seems to kind of tap out at these higher kind of consistent rates. And something that we're going to get back to is understanding a little bit more about bubble number density. All right, so those were my brief kind of overview of some of the petrologic tools that we have. And now I want to highlight some of the challenges that we have with these techniques. Now, the first being that there seems to be this offset in range between the different methods. Here on looking at the Shea 2017 kind of compilation, we see melt and bayment seem to produce rates that are similar to microlights, but these all seem to be rates that are much slower than what we see in conduit models. Again, looking at this Hijra-Marza et al. 2021 study, we can see that bubble number density is also giving rates that, if we plotted it over here, would be right around 100, that are much faster than other independent geospeedometers. So the question then becomes, well, do we trust all of these? Do we need to do more work to understand what they're really recording? Or if we do trust them and we feel like that they are representative of what's happening, are they then just representing different regions of the conduit systems or skewed to potentially specific rates? For instance, melt and bayments cannot record rates that are much faster than what is shown here. So potentially conduit models are at rates that are not going to be recorded due to the limitation of water being able to diffuse into a bubble and record that process. So again, I think it's important to start to recognize that these can be rate limited recorders, meaning that if you take one study where you look at microlights and another study where you look at melt and bayments, you might not be able to compare the rates that you're extracting at them directly to each other. So long as you have some idea as to what they are responding to in the conduit system, then potentially you can start to compare apples to apples. A nice summary diagram that I think illustrates many of the points that I want to make in the talk today is by Cassidy et al. In 2018. What you're seeing here is on the y-axis ascent rate and decompression rate, and on the x-axis is different compositional regimes. Each of the symbols is relating to a different petrologic or experimental monitoring tool to use to extract decompression information. Everything in black is representing explosive eruptions, and everything in red is representing an effusive eruption. So the first point that I want to highlight kind of following up on that last slide, is that if you look at things like diffusion modeling, well, diffusion modeling tends to always give you timescales associated with explosive eruptions. Whereas if you look at something like microlight number density, these tend to be associated with effusive eruptions, which again highlights that these different tools are going to be weighted to certain ascent conditions. You can see on this diagram that there is kind of this nice break between explosive and effusive phases. But I think another really important thing to highlight is there's 9 orders of magnitude represented on this diagram. So magma decompression rate is not the most simple thing to be able to extract from these systems. And it is probably unfair to expect any particular petrological tool to be able to span that entire range. Another point I want to make on this diagram is if we look at things like Mount St. Helens, any volcanic system can have up to 6 orders of magnitude of decompression rates associated with it. But that doesn't mean that that's representative of the full range that can happen within a system. If we take Yellowstone, for instance, and we see that there's 4 rates associated with it, 2 for effusive and 2 for explosive. If you were to model an explosive eruption, you likely shouldn't just take this rate as this is an explosive eruption from Yellowstone, which is this like very dynamic system. And in personal experience, I've worked on systems where you can have 3 orders of magnitude of variation in ascent rate within the same fall deposit. And so really this is not a simple single rate can be applied to any particular system situation. And you have to kind of embrace the nuance that you can have this really large shift of rates being preserved within any volcanic episode and even more variation within any volcanic system. So the several orders of magnitude represented by any volcano, and not to mention the variation which can occur in eruptive sequence. This is something that I think from a field geologist perspective really needs to be taken into consideration when creating things like numerical models to try to understand the dynamics of that eruption. So for instance, it wouldn't be a talk from petrologist or a field geologist if there weren't some field photos. So just looking at these 2 deposits on the left-hand side, the upper one is the late Bronze Age eruption from Santorini, and the lower one is an eruption of the Huckleberry Ridge Tuff from Yellowstone. What I want you to notice here, especially with this upper one, is that you can see a lot of variation that is occurring within this fall deposit, which is all containing really important information on how magma decompression and ascent has evolved over the course of this eruption. So if you were to take one, sample from the coarsest area of this deposit, it would only be representing magma ascent and the dynamics associated with this phase of the eruption. Importantly, if you look at the very base here, you can see this fine layer of material. And then there's kind of this darker break, and then you see this kind of upward coarsening as you move through this deposit. Interestingly, after this kind of opening phase, this is thought to be a precursory phase where there's actually evidence from the people that lived on Santorini at this time that they escaped, that there was a long enough pause between this opening phase and where the rest of this material comes out, that they left the island and there's no evidence for any bodies being preserved in the eruption that follows. So intriguingly, this, going back to Eleanor's talk, well, what does this mean about dike opening deep within our conduit system and to be able to shut this off and then turn it back on again? And so really coupling the intricacy of the field data with the petrologic tools, I think can allow us to better understand what's happening in that conduit system, which is our ultimate goal, is to try to really understand what is controlling magma ascent rate and reconstructing these different regions of the conduit system. Again, this lower photo from the Huckleberry Ridge Tuff, you can see evidence for wind interaction and rain interactions, suggesting that the plume started and stopped multiple times at the onset of this massive 2,500 cubic kilometer eruption. And so that again brings up the point, well, how do we model and understand the nuances that these field deposits preserve when there's all this evidence to suggest that the conduit may have been slow to develop, or potentially even how do we think about it from a field petrologist point of view when we always envision it as being a conduit, but as Eleanor nicely emphasized, you can have several conduits. So how does that complicate our understanding of these deposits? One example that I think is a really nice way forward, including some of the examples that Mattia suggested of coupling crystal size distribution and bubble number density with numerical modeling. This is an example from Masser et al. 2018, where they had extensive field data for understanding things like mass discharge rate, the thickness of the deposit, the grain size of the deposit. And so what they did was to try to couple a numerical model to recreate the dynamics of that field deposit. And in this model, what they did was allowed there to be a deep dike feeding system feeding into a narrow conduit system. Some of the interesting things that they found from this study was first that they needed quite an extensive dike system that would evolve over the course of this eruptive sequence in order to recreate kind of the mass discharge rates that they were inferring from the field deposit. The next really interesting thing from this study was that they suggest that magma spends a longer amount of time in this deep dike system feeding into this narrow conduit system. And rather than just coming directly from the magma chamber, that there might be this intermediate stage. And this is a kind of an idea that I'm going to come back to in a little bit. So again, I think that moving forward, it's really interesting to try to pair field studies and petrologic studies with numerical models to try to learn more about how the evolution of that conduit system and that multi-phase flow is evolving. But of course, that is a complicated question, as Mattia nicely laid out. All right, so the other topic that I wanted to address based on this Cassidy compilation and Shea 2017 is that many of these speedometers are only reacting to maybe specific areas of the conduit system or only recording specific rates. So what do they really tell us? How do we know how to interpret them and what areas of the conduit system they're responding to? So I'm going to give you an example from my own work where we attempted to compare multiple different decompression proxies to understand the evolution of a volcanic episode, as well as to see how they compare to each other. And this is an example from the late Bronze Age eruption from Santorini, that deposit I showed you where you have this opening precursory phase. The first step that we took was to break up the field deposit into multiple different horizons that we could trace around the vent system, allowing us to reconstruct isopac and isoplep maps. This then gave us information on mass eruption rate and plume height, which you can easily kind of guess that you're going to increase towards the coarsest area of your fall deposit and then potentially decrease during the formation of pyroclastic flows. What was unique is that we then decided to take single POMAS costs from each of these horizons and apply both bubble number density as well as melt reentrance to understand how all three of these proxies are behaving during the course of this eruption. So this is a lot of data, so I'm going to slowly kind of walk you through it. In that melt reentrance are shown in triangles, whereas bubble number density is shown in these circles, and the difference between heterogeneous and homogeneous nucleation is kind of emphasized. The first thing I want to kind of point out is that melt reentrants are about 2 to 3 orders of magnitude slower than what we're getting from bubble number density. And this again pairs really nicely with other studies that have highlighted that bubble number density seems to have these very fast decompression rates. The other interesting thing is that both melt reentrance and bubble number density show a much more sinuous path compared to mass eruption rate, especially right at the beginning where you see that they both decrease. Interestingly, from the field deposit, we see this as a fine ash layer, suggesting that maybe unlike mass eruption rate, which is limited by looking at the deposits and having to apply this lithic measurements, both melt reentrance and bubble number density can react very quickly to changing conduit conditions, meaning that if ascent rate starts to slow down, which might be preserved as an ash layer in the field, they could be recording this process and used to inform on how the conduit system and mass or decompression rate is evolving over time. Another interesting thing from this data set is that we see that melt reentrants don't seem to match at all with what we're seeing for mass eruption rate, whereas bubble number density seems to be kind of mimicking a little bit more the mass eruption rate we see in this deposit. And so what I think importantly this suggests is going back to understanding the rate limited processes of this system, that melt reentrants as you start to approach the fragmentation threshold, you typically from numerical modeling see that you accelerate, and Mattia emphasized this really nicely, you accelerate by about 2 orders of magnitude as you approach the fragmentation threshold. So melt reentrants are going to start diffusing and recording magma ascent once exsolution begins somewhere deep in the conduit system. And as you approach the fragmentation threshold and acceleration of that material occurs, they're no longer going to record that process. Whereas bubble number density is really thought to have this second nucleation event as you approach fragmentation. And so it might be weighted more towards this steep pressure gradient that is forming in the system. This would be probably a fair time to honor the fact that from the petrologist standpoint, we typically model the processes that we're interpreting based on constant ascent from the storage region to the surface. Although we know from conduit modeling that this is not the case, that you see this acceleration as you start to approach the fragmentation threshold. And so this is potentially an area where petrologists can work to step it up in that we are maybe making simplifying assumptions in these models that are not necessarily the full understanding of what is happening in the system from other independent methods. All right, so back to this data, I think what this is suggesting is that we actually are preserving evidence for decoupling between the upper and lower conduit processes, that the reentrants are recording deeper in the conduit system and bubble number density, at least in this particular example, is recording closer to that fragmentation threshold. The advantage is that if we continue doing these kind of studies where we couple multiple different tools for understanding magma decompression rate, we might be able to learn more about what is happening within that conduit system and potentially even use this information to constrain numerical models to improve our understanding of how conduit might control these shifting dynamics. So similar to that Macero model, could we put in some of the data from multiple different petrological proxies to constrain those models? So this is something that actually Mattia kind of beat me to, but reconcile and bubble number density. This great study by Hisham Marza et al. 2021 essentially points out that, we all have seen bubble number densities being at much faster decompression rates than other independent geospeedometers. And so confirming kind of this idea that I just presented, in that typically these rates are weighted towards that last area, that last region of the conduit system. However, to get to those rates, you had to go through this whole magma ascent process. And so what they did is they time averaged the entire ascent process, which then allowed them to use bubble number density to reconstruct a decompression timescale that now overlaps with other independent geospeedometers. Meaning, again, that we have to really investigate what region of that conduit system are these different speedometers recording. All right, the last thing that I want to kind of touch upon from the petrologic perspective is this idea of multi-stage decompression. And so just like the Macero study, which required this deeper dike system feeding into a narrow conduit system, there is evidence from other systems, including melt reentrants, that there's multi-stage decompression, meaning a slower initial ascent followed by a more rapid ascent process that's occurring within these systems. And so this is an intriguing idea, suggesting that this conduit system is a much more dynamic, and potentially you can use these different petrologic tools to comment on different regions. Going back to Diana's talk on Tuesday, she presented this figure, which also emphasizes this idea that potentially we have these 2 stages of magma ascent in numerous systems. And so from this diagram, each of these black diamonds is representative of an earthquake, where these red lines are an eruption. And the region down here, this red region at the base, is associated with magma storage. And so in this, they essentially see that there is kind of a disconnect between where most of the seismology and seismic events are occurring prior to these eruptions, where you then, during the eruptions, you see seismicity associated with the full length of the conduit system. And my favorite kind of interpretation for what they think is happening within this system is that magma is ascending so slowly to begin with as to appear to be aseismic. Again, suggesting that potentially magma ascent from the storage region at the beginning, as that dike is forming and moving towards the surface, is quite slow, and that you might be separating that within a numerical model or into our petrological understanding of these systems prior to the kind of faster final eruptive period. All right, so in conclusion, the ponderings of a petrologist, field volcanologist, ascent rate is not a single number for any eruption. There can be orders of magnitude variation within a deposit, and I think by embracing this and applying multiple tools, we might really start to learn more about these conduit systems. We do, of course, have to always evaluate the limits and assumptions of each petrologic tool. Applying only one might only allow for specific rates to be retrieved, and so we might need to actually apply multiple of them to understand where those limitations are occurring. And importantly, these tools can be coupled to reconstruct more details on the ascent process, including bringing in things like numerical modeling. And now we decided as a collective, the four of us, Diana, Eleanor, Mattia, and I, that we wanted to give some ideas and final takeaway messages on magma ascent. The first one, of course, is something that's probably said in every workshop. We need more experiments to constrain variables within individual communities, meaning that we need experiments to constrain diffusion coefficients for modeling petrology, but you also need experiments to understand the rheology of rocks within kind of deep fracture zones. Applying petrologic and numerical modeling tools to eruptions that have geophysical and seismic data might help to bridge the disconnect between these techniques and create a more integrated understanding of process. This, of course, I think is the goal of many of our communities right now. I don't think this is like a novel idea, but it is important to caveat it with the fact that we are then kind of skewing ourselves to lower VEI eruptions, and that we might have less of an understanding still of like higher VEI, more explosive events. One thing that we really enjoyed is we met several times to talk about magma ascent, and we really found a lot of perspective in the interdisciplinary nature of our group. And so one suggestion that might spur off of this initiative is to form interdisciplinary working groups focused on particular regions of the conduit or storage system. Example, fragmentation, having people from multiple perspectives that are really interested in fragmentation get together and have to work to explain their science to each other, figure out what kind of details are needed to constrain one or the other model, and we might make quicker advances in this way. And then lastly, closer collaboration with industry who have great models constrained by ample data sets that often could behave as analog models for different features of volcanic systems. So with that, I'll take any questions.
All right, thanks, Madison. That was a great talk. We have a question from Patrick Bobbitt, who asks, when in the field, how much consideration do you put into the effect that local topography might have on the deposits in place from PDCs?
Well, obviously, local topography is going to have a huge effect on PDCs. I don't know if that necessarily would alter my strategy for trying to reconstruct magma ascent timescales, because typically you're taking a clast and you're representing it, taking the data from it to represent some part of its eruptive phase. And so I think they're somewhat decoupled. I don't know if you have any follow-up on that. Whatever this was. I can't really see questions. Here we go. Oh.
Great. Yeah, we have another question coming in from Karen Bemi. sorry if I mispronounced your name. When you suggest collaboration with industry, what industries are you thinking about?
This is where I'm now speaking for the group. So this was mostly Eleanor's idea, but I think the idea behind it was, for instance, there was evidence in Italy for like a salt dome collapse that she was suggesting would have models that were indicative of processes that would occur within volcanic systems. And so I think the idea would be systems where they work in hydrofracture was her suggestion, because the models that they have developed are based on larger data sets and might have not simplified some of the things that we have in our numerical models. But Eleanor should feel free to correct me on that one.
All right, well, given that it's 1/2 the hour and I don't see any further questions in the box, I think we'll go ahead and conclude at this point. As a reminder, these talks have been recorded and they'll be placed on the MCS RCN website by next week. So as a reminder, as Helga mentioned, we're going to have a meeting tomorrow at noon Central Time, and that's going to focus on how a model collaboratory can be used to address some of the science questions that have been raised today and throughout the webinars that we've had so far. We're starting to build the potential form of a collaboratory now, so this is really your chance to give input and start to shape that proposal that ultimately hopefully comes out of this. Everyone is welcome, so please go ahead and sign up on our website. As a reminder, it is in fact a separate registration, so the one you got today is not going to work for tomorrow. Our next series of webinars is focused on integrative volcano modeling and forecasting, and that's going to take place in early May. Again, please see our website for details on that. And with that, thanks to everyone for joining today. Thanks to our moderators, and in particular, of course, thanks to our speakers who volunteered so much of their time in putting these really good talks together. So thank you all, and see you next time.